folks, this is Will with SRT Amplification, and in this video we're going to check out a couple of things. One, we're going to look at what a balanced input is in audio gear and how it works, and the other is what an operational amplifier is and how it works, otherwise known as an op-amp. In a previous video I actually repaired an XLR socket, which is used as a balanced input in a lot of pro audio gear, and I didn't really go into explaining exactly how the whole system worked and how it did what it did or why it was even used. So I kind of left that out of that video in order to do a dedicated video on these two items by themselves. So this is that video, and I hope you enjoy it. Okay, so what is a balanced input exactly, and why do we need it? Well, in the audio world, you know, you have basically really small signals that are generated from different things, guitars, microphones, all kinds of stuff are being used to produce a signal. And those signals have to get to a device that amplifies that signal and ultimately turns that signal back into something that you can hear in a speaker. And we want that signal to be as clean as possible. So normally, you know, in a normal guitar cable, it's so short, and it's usually between, you know, the amplifier and the guitarist, and there's not a lot of things in between him and the amplifier to cause a lot of noise or whatever. But whenever you're running signal lines, cables across, you know, bundled up with each other, and a whole bunch of them going to mixer boards and stuff like that, across the stage, past AC outlets, lighting, all kinds of stuff, and over long distances, like maybe from the, you know, the back of the stage all the way back to the or to the front, where they have the mixer board and all that stuff in the, you know, the front of the auditorium or the theater or the arena or whatever they're using. You have a chance of a lot of noise getting picked up on those cables. So what they've done is, with the balanced input, is basically they have the source produce two signals. One is the original signal, as you see here, and the other one is a negative of that signal, or inverse of that signal. It's basically 180 degrees out. It's just a mirror image, basically. At whatever point this is high, this one is the same point but in the negative direction, and vice versa. So basically what ends up happening is you have two signals, so you need two signal carriers, and the, you know, the shield slash return reference, whatever you want to call it here. In a normal guitar cable, you only have one signal conductor and the shield, so you can't get a balanced input off of that. We'll talk about different connectors that we can use for balanced inputs here in a minute. But in a normal mono jack type of situation, all you have is just one cable and the shield. But in a 3-wire system like this, basically any noise that comes across this cable and gets induced into these conductors here will be in phase with each other because they're cutting the conductor at the same time. So now we have an in-phase noise signal on both of our lines, if there's any noise induced, and two out-of-phase signals that we're actually wanting to reproduce here. So we use a special type of device to get rid of this noise, and one of the things you can use is what's called an operational amplifier, or what's normally referred to as an op-amp. Now, it's called an operational amplifier because it does amplify, and they're very good amplifiers, as a matter of fact, but they're hard to tame. You have to do something with them, and we'll look at the schematic later about what you have to do to these to in order to get a signal out that, you know, that reproduce it correctly. So fidelity is what the term for that is. But anyway, in this case, we use this type of operational amplifier. It does mathematical operations, is what it really does. You can use these things to become summing amplifiers or differential amplifiers, or differentiating, or integrals, or You can use them for oscillators, all kinds of things these amplifiers are good for. But in this case, we're using it as a differential amplifier. And basically, on an op amp, there's two different inputs. There's a inverting input and there's a non-inverting input. The non-inverting input basically takes the signal as it sees it. The inverting input takes the signal and inverts it 180. So when it sees the signal here on the bottom in the annotated by green, it's going to flip that back over, and basically the two input signals at that point going through the op amp, as the op amp sees it, are the same. So it passes it out just like it sees it. It may have a little gain, a little amplification to it, but really it's just passing it out. And then what happens to the noise as it enters the inverting side of the op amp? It gets inverted on one of these legs, and now they basically become mirror images of each other. And to the op amp, it basically, when it sums it up, it's a sum zero. So you basically have nothing going out the other end. So you get rid of a lot of that noise that is induced here. So you just have this clean signal coming out. So how can we make a balanced signal line? Well, you can do it with a 1/4 inch jack plug, like your normal stereo plug, in which the tip and the ring are going to be your signal carriers, both non-inverting and inverting signals, and then your S right here on the end is going to be the shield. Or you can have an XLR type of cable. These are or connector. These cables will basically usually have male pins that will fit inside these female receptacles or sockets, and it does the same thing. The 2 and the 3 will carry the signal, inverting, non-inverting and inverting, and the 1 will be the shield or the return. So this is the component that I replaced in that Peavey mixer amplifier, and it was what was off. It was what was messed up, so I had to actually repair it, and then I actually resoldered all of them. But as far as the XLR connectors go, they come in various shapes and sizes, and I don't really want this to be a history lesson, but these things were originally invented by a guy by the name of James Cannon. That's 2 ends, not 1 end like the Canon cameras. But there's a little bit of mystery behind these things. He invented them back in the 50s, but they didn't start becoming widely popular in commercial audio gear until probably the late 70s, early 80s is when you started kind of seeing them. And then by the 90s, well, they were just about on everything. There's been a lot of improvements made to them over the years. They come in 3 pins all the way up to 7 pins. They're not only used for audio, but they're also used as like MIDI controls now, lighting, all kinds of things. But the mystery behind them is what XLR actually stands for. And if you go on the internet, you're going to find a whole bunch of definitions from different places. Some are going to say that it means external line return. Some say that the X means no signal. The L means live signal, and the R means return signal. You'll see some places that say that it stands for extra low resistance, which there is a kind of a connection with that, because on a balanced input in audio amps, usually the balanced input is a low impedance input, but that has to do with the actual circuitry of the input itself and not anything to do with the cable or the connectors or anything like that. However, these cables do, because they are ran such long distances, they do have a lower resistance than like your normal, everyday guitar cable or something like that. So that kind of stands true a little bit, but that's not the what I believe the actual nomenclature or what XLR stands for. The best explanation that I've seen on it, and I believe this to be the truth, is that back in the 50s, the Canon Electronics Company was using a connector type that was called the X series, and when James Canon modified the X series to make the XLR, what he did basically is he added a latching mechanism like this right here you see in the picture, and they were made out of some kind of molded rubber at the time, which now you get them in metal and plastic and all kinds of things. But the L stood for the latching mechanism and the R stood for the rubber, and so then you had your XLR connector. So I believe that to be the case. I believe that to be true. Has nothing to do with anything else except for the design of the actual plug and socket itself. So with that being said, let's look at the schematic real quick and check that out. Okay, so I basically have this Peavey XR680C mixer schematic basically zoomed in here to the channel that I'm going to talk about here. Basically, this is the input, the XLR input. So, and it's basically got 8 channels, so there's eight of these. They don't show it on the schematic because they're all the same, but basically this is just showing you one of them, and they're all going to be identical. But basically you can see here that it's got J1 designation for the first socket, and it says low Z input, which means low impedance. And that's just talking about its impedance to ground as the amplifier sees it. So one thing to note on this is this pin number 1 is tied to the chassis ground, which is a common that runs all the way down the bottom of this, which is not the same point as ground, because there's an actual 10 ohm resistor between this line and ground itself. So there's a difference of potential here, possibly. So it's just worth noting on that. If you do any testing on this, this is not the same point as ground electrically. So what we want to look at here is this op amp right here. This is the symbol for an op amp. It's just a triangle, and this is actually 1/2 of a 4558 dual op amp IC chip. And this 4558 basically serves as you'll see in the video. I'll actually pull one out here in a little bit. I'll show that. But it basically serves as the differential amplifier for 2 different input jacks, 2 different XLR inputs. So J1 and J2 would be served by U1, and you can see it kind of gives you the explanation on how this is. This op amp has 8 pins. Pins 4 and 8 are the positive and negative 15 volts for each op amp. So these are shared between the 2 op amps. And then pins 6 and 5 are the inputs for J1. 7 is the output for J1. 2 and 3 are the inputs for J2, and 1 is the output for J2. So that's basically your pin out in a nutshell right there, 1 through 8 on that op amp. Basically what's happening here is, like I explained earlier, that inverted signal that's coming in on pin 2 comes into the inverted side of the op amp and it gets flipped over. The original signal comes in on pin 3 and goes into the non-inverting side, and then your signal's passed. Any noise that was induced on this line as it went out is going to be canceled out in this particular thing, in this particular op amp. Again, one is tied to the shield here, to the chassis, or the common point. Whatever they're using here is a common point. Basically, this is being set up as a differential amplifier. It has a positive feedback loop and a negative feedback loop. This negative feedback loop is going to basically give it whatever gain value that this op amp has, which is going to have a little bit of gain. I can see here I got a 10K resistor here in my feedback loop, and my input signal had, 100 or 1,000, 1,600, almost 1,700K coming in. So it's the ratio between these that's going to determine the gain. So it will have some gain on this side right here. That's going to be its first gain stage in the preamp section, basically. But more importantly, this is taking the noise out of the circuit. Okay, we're going to see in the non-balanced input that the op amp is not set up this way. So let's go over here to the non-balanced side real quick. Okay, so as you can see here, this is your 1/4 inch jack, and when you insert, or your 1/4 inch socket, when you insert a 1/4 inch jack into this, it's basically going to lift up this little springy metal piece right here in the jack, or in the socket, and it's going to lift it off of this circuit. So this circuit's going to be completely isolated. It's going to be taken out, basically. And so you're going to be inputting the signal here on pin 3, which is the non-inverting side. And notice you don't have a signal being applied to the inverting side of this op amp. Basically, this is just the negative feedback that's going to get you the gain, whatever gain is being determined by this. I could work out the calculation and tell you what the gain is exactly. But this is going to be your first preamp stage. And actually the gain on this stage is going to be determined by this potentiometer right here, or this level potentiometer. So you can actually change the gain of this op amp. It then goes on to some more stages. The signal is also bypassing this particular op amp here and going to the next one for your monitor, in which you basically have the same controls as you had with the level, but the monitor is going to come out and go to the monitor bus, which is out here, and it's going to skip a lot of these other stages like your tone controls and all that stuff. It's just going to go straight out to your monitors. Whereas your main signal is going to come out, bypass that monitor circuit, and go straight into another preamp section. And that preamp section, at that point, it's going to be inverted. The signal coming out of here is going to be inverted, which it'll be put back shortly, but it's going to be inverted. And you can see with this, we're also setting up another negative feedback loop with this 47K resistor and this 22K resistor here. So that's going to be setting up the gain for this stage. We're going to go through a tone network here with our low, mid, and high pots, and then there's going to be some losses there, so we're going to recover that here in this op amp right here. Again, this op amp has another negative feedback return path, and that negative feedback return path basically goes through that tone circuit. So it's going that the gain of each type of frequency is going to be determined by this network right here. So you can actually take out highs, lows, frequencies, and all that stuff based off the values of these capacitors and these resistors here, these potentiometers. So you basically set up the tone shaping in this right here. You're going to have another level of amplification, and then this amplification goes out to the main bus where it goes to the power amplifier and gets amplified and outputted to your speakers. Okay, so one of the other advantages of having these type of balanced inputs or whatever is with this type of system, I can put phantom power out to devices. So you can see right here, there's another part of the schematic where there's a phantom power 48 volts more than likely is going to be applied to this point right here, and I can inject that here on pin number 3, and I can run phantom power out to the device like an active component of some sort, or a condenser microphone, or something that needs 48 volts in order to operate. I can run that 48 volts there. There'll be a switching mechanism to put that voltage on this line right here. So that's one good thing about this. One thing I wanted you to pay particular close attention to is this little area right here. A lot of manufacturers do this with their amplifiers, and I've never liked it. I don't think it's a good design. I think they can do it other ways, but this is probably the cheapest way. I'd rather see some kind of relay mechanism or something like that. But basically, what happens is when you use the balanced input signal, the balanced input socket, the XLR socket, you rely on the connection, this little connection right here. And so if this little metal piece in the 1/4 inch socket doesn't spring back and make connection to this piece that's stationary, or if there's any corrosion between the leaf and that stationary point, you may not get signal or adequate signal past to the next stage. So that's a big disadvantage. So make sure, especially, you may tell yourself, okay, I'm only going to be using the XLR connections on this amplifier, so I don't care what these 1/4 inch jacks look like. I'm not even going to clean them up. Well, you were relying on that 1/4 inch jack or 1/4 inch socket to make that connection, so you definitely want to make sure that this area right here is clean. Yes, it's a very high failure point. Also, you'll see in the video that I'm about to show me taking one of these 4558s out. Normally these are socket mounted. In other words, they're not directly soldered to the board. You can actually pull them out. That's another high failure rate. These end up getting damaged or destroyed, and you can just replace them. They're real cheap. You can just plug them back in. You don't even need to solder anything. You can just pull them out and plug them back in. So that's probably, if I have good signal with a 1/4 inch jack, and I pull the 1/4 inch jack out and I don't have good signal with my XLR, the first thing I would look at is this connection point right here, and then I would focus my attention on this op amp. Check the signal going in, signal coming out. You see the pin numbers, you can check those and determine if it's actually passing signal or not, and then go from there. But that's really all there is to this thing. In the preamp section, like I said, they're all exactly the same. You do have an effects bus that goes out and all that stuff. This is for your reverb and everything like that, and they're all the same. You got one of these for each channel. So that's just going to introduce more or less reverb into your signal. So it's pretty simple. That's basically balanced inputs in a nutshell, and how they work and why we use them. So I hope you enjoyed this video, and if you have any questions, please put them down in the comments below and let me know, and anything you want to discuss, and I'll be happy to discuss it. If I missed anything or I said anything that was incorrect, please let me know that too. I'm always wanting to learn new things and better myself in these endeavors, and I appreciate you viewing. Thank you.